Okay, in this video, we're going to talk about suggested homework problems from 7.4, where we talk about arc length and surface area integrals. Let's go ahead and get started, and you'll see the setup of these integrals as we go along. So, first question here, what is a rectifiable curve? The graph of a curve is rectifiable with the function f, let's say it's rectifiable between the points a, f of a, and b, f of b, if f prime, the derivative of f, is continuous on the interval a to b. So, long way to say that the function is continuous and differentiable on this interval, because we know that differentiability is going to imply continuity, and that the function f prime is also continuous on the interval. So just saying that the function f prime is continuous on the interval, make sure that f is also continuous and differentiable on the interval. So all that must be true for us to be able to find the arc length of something using this formula. Since we're using a definite integral as part of the formula, we have to have a derivative that is continuous on a to b. Okay, so let's go ahead and look at number 3. And before we look at number 3, let's talk about what our arc length formula is. So s, lowercase s, is equal to the integral from a to b of the square root of 1 plus, and I like to use y prime for this, squared, or, and this is dx if we do that, or s is equal to a to b of 1 plus x prime squared dy. So this is, we can say, let's call this f prime of x to be consistent with what we just did before that. There we go. So if y is equal to f of x, then we want 1 plus the derivative of f of x squared inside the square root sign, inside the integral from a to b, and integrate that with respect to x. If x is a function of y, we want the integral from a to b of the square root of 1 plus f prime of y squared dy. So now let's look at the question number 3. Says we have 0 to 2, integral 1 plus quantity 4x squared dx. We're following this first form. So f prime of x is equal to 4x. That means that f of x could be any solution to the indefinite integral of 4x dx. That would mean f of x is equal to 2x squared plus c. So The easy answer, the most elementary answer to this question of what function could f of x have been here would be 2x squared, but really any answer that adds a constant to 2x squared would also work. It's that entire family of answers that's possible, as long as they are, well, they will all be continuous and differentiable on the interval from 0 to 2 because they're polynomials. So let's go ahead now and look at number 5. Number 5 says 2, 1, and 5, 3 are points, and we first want to use the distance formula to find the distance of the line segment that connects these points. So to do that, our distance formula d is equal to the square root of delta x squared plus delta y squared. Delta x is 5 minus 2 is 3. Delta y is 3 minus 1 is 2. So d is the square root of 3 squared plus 2 squared is the square root of 9 plus 4 is the square root of 13. Now, for part B, I'm going to need that for a line, f prime of x is equal to the slope delta y over delta x, just in a linear equation like this, so I don't need to find the whole equation of the line. So that's going to be 2 over 3. So s is equal to a square root of 1 plus 2/3 squared, integral from 2 to 5 x dx is going to be, this will all be a constant, so s is going to be the square root of 1 plus 4/9 integral dx is equal to square root of 9 plus 4 over 9 x from 2 to 5. S is root 13 over 3. 5 minus 2 is root 13 over 3 times 3 is root 13. So we get the same answer both ways. That is only going to work, the first method is only going to work with line segments. It's not going to work with curves. So now we're going to get into some curves here. And we want to say y is equal to 2/3 x to the 3/2 plus 1 makes y prime equal to x to the 1/2. And s will be equal to integral of 0 to 1 is what's outlined in black there. Square root of 1 plus x to the 1/2 quantity squared dx, integral 0 to 1 of x plus 1 to the 1/2 dx is x plus 1 to the 3/2 times 2/3 from 0 to 1. It's going to be 2/3 of 2 to the 3/2 minus 1 to the 3/2 is 2/3 of 2 root 2 minus 1, 2/3 2 root 2 minus 1, just to get an approximation here, since we probably want an arc length that we can express to people. And this will be, see, I think I'm going to 3 decimal places here, 1.219. That's my approximation. So now at number 11. 11 says y is equal to 3 halves x to the 2/3. And now my interval is 1 to 8. Y prime is equal to 1x to the negative 1/3. So s is equal to the interval 1 to 8 of the square root of 1 plus x to the negative 1/3 quantity squared dx will be 1 to 8 square root of 1 plus x to the negative 2/3 dx. I don't like negative exponents inside of my square root, so I'm going to multiply by x to the 2/3, top and bottom. And then I'm going to split my integral top and bottom. And then I'm going to bring this one up as part of my du. U is equal to x to the 2/3 plus 1. U prime is 2/3 x to the negative 1/3. And so I'll throw the dx over here on the end. I want to make this 2/3 and balance it with the 3 halves. And then I have s is equal to integral of u to the 1/2 du. Change my u values. 1 plus 1 is 2. 2 squared is 4 plus 1 is 5. So this will be 3 halves on the outside there. And so that will be 3 halves u to the 3 halves times 2/3 from 2 to 5. And these will cancel. S is equal to 5 to the 3 halves minus 2 to the 3 halves, or 5 root 5 minus 2 root 2. So 5 to the 3 halves minus 2 to the 3 halves. S is approximately 8.352 when I go to the nearest thousandth for my estimate. So now at number 15. Y is equal to ln of sine of x. We're on the interval of pi over 4 to 3 pi over 4. Y prime is divided by sine. This is cosine. Cosine over sine is cotangent. So s is equal to integral pi over 4 to 3 pi over 4, square root of 1 plus cotangent squared x dx. 1 plus cotangent squared is the same as cosecant squared, using a Pythagorean identity. And then that square root and that squared will make each other go away. That happens a lot with trig functions, that we use Pythagorean identities to rewrite to get a perfect square underneath the square root and then make the square root go away. Now we just learned about the integral of cosecant recently, so that's a negative ln of cosecant x plus cotangent x, or you could write that with the minus inside there instead of the plus. Your choice. This goes from pi over 4 to 3 pi over 4. And then I'm going to look at my unit circle here to help. I'm at pi over 4 and 3 pi over 4. And I'm going to use the unrationalized versions here, that this is 1 over root 2, 1 over root 2. And this is negative 1 over root 2, 1 over root 2. That'll help me to reciprocate these to find cosecant and cotangent quite easily. So S is a negative ln of the absolute value of reciprocal of sine of 3 pi over 4 is going to be root 2 plus cotangent of 3 pi over 4. So that's going to be cosine divided by sine. That's negative 1. So minus 1. And then minus a negative is going to be plus ln. Absolute value of cosecant of pi over 4 is root 2. And then cotangent cosine over sine is plus 1. So that is enough that I can plug it in like that, but I'm going to remind you of some pre-calculus stuff that you can do here. And this is root 2 plus 1 over root 2 minus 1 because of properties of logs. And then I can rationalize the denominator and make this root 2 plus 1 times root 2 plus 1 over root 2 minus 1 times root 2 plus 1. All of this is, if you want to say bonus content, you could have just plugged this into the calculator to get your estimate, but I'm trying to get the most simplified exact answer for you. So root 2 times root 2 is 2. And then you have plus root 2 and plus another root 2 and plus 1 in the numerator. And then we have 2 plus root 2 minus root 2 minus 1 in the denominator. Root 2 zero each other out, which was the whole goal of that. 2 minus 1 in the denominator is 1. In the numerator, 2 plus 1 is 3 plus 2 root 2. So S is exactly equal to ln of 3 plus 2 root 2. I realize at this point that I don't need my absolute value bars because it's going to be a positive value. When I add 2 root 2 to a positive 3 up to this point, I wasn't sure and I had those absolute value bars, but now I know for sure that I don't need them. So let's go ahead and approximate this now. Ln of 3 plus 2 square roots 2 is 1.763. Let's look now at number 19. X is equal to 1/3 y squared plus 2 to the 3 halves. Bounds on y are 0 to 4 included. So this tells me this is an x as a function of y situation. I'm going to be finding x prime, and that's going to be 1/3 times 3 halves y squared plus 2 to the 1/2 times the derivative of the inside is 2y. 3's will cancel, 2's will cancel, and leave me with x prime is equal to a y times y squared plus 2 to the 1/2 power. So S is going to go from 0 to 4, square root of 1 plus y squared plus 2 to the 1/2 quantity squared dy. S is equal to 0 to 4 root 1 plus y squared times y squared plus 2 dy. S is equal to 0 to 4 of root y to the 4th plus 2 y squared plus 1 dy. You may recognize this as a perfect square trinomial in the form of a squared plus 2ab plus b squared, where a is equal to y squared, b is equal to 1. So S is equal to 0 to 4 root y squared plus 1 quantity squared dy. S is equal to 0 to 4 y squared plus 1 dy. I don't need absolute value bars when I take the square root of a perfect square because I'm always in positive values here for my S. Watch out for that though, if it's possible that this thing could take on negative values. Remember that the square root of x squared is actually the absolute value of x. So we're going to say S is equal to 0 to 4 y squared dy plus 0 to 4 dy. So S is 1/3 y cubed, 0 to 4 plus y, 0 to 4. S is 1/3 of 4 to the third plus 4. The zeros aren't going to do anything, so 64 over 3 plus 12 over 3, since 4, I'll multiply by 3 over 3, and that becomes 76 over 3 for my final answer for my arc length for number 19. No approximation really needed for that. Moving on to number 21, I'm going to do all three parts, even though A and B were the only parts that were assigned. 21, down here, y is equal to 4 minus x squared on the interval 0 to 2. Sketch a graph of that for part A. Have a y-intercept of 4. We have an x-intercept of -2. We have an x-intercept of 2. And it's my best attempt at drawing that curve. Now I'm going to trace the part of the curve in a different color that I shall highlight here where I'm interested in. 0 to 2, right there, that part is what I'm interested in finding the arc length of. So let's go ahead and write the integral for that for part B, and that's going to be 0 to 2. Let's see, y prime is going to be a -2x, so root 1 plus -2x quantity squared dx. 0 to 2, root 4x squared plus 1 dx is not something that we can solve by hand with the techniques that we know right now. We will learn something later to help us possibly take care of integrals that look like that. But for now, if we were to do part C, we would have to use the integration capabilities of the calculator. Let me show you how to do that. Math, functional integration, 0 to 2, and then square root of 1 plus 4x squared dx, like that. And then going to enter. And this is approximately, this is my answer for part C, 4.647. I go to the nearest thousand. All right, let's look now at number 25. Same instructions, A and B are what's suggested. I'll do part C just to show you how to use the calculator. Y is equal to sine of x, y prime is cosine of x. Part A, sine looks this. And then pretty bad at drawing right to left. Not that great drawing left to right either, but better. All right, and then we're interested in the interval of 0 to pi. This keeps going on this end. This keeps going on this end. Grab my highlighter. 0 to pi is this bit right here. 0 to pi between those first two x-intercepts on the right. So we have s is equal to interval 0 to pi square root of 1 plus cosine squared x dx. Again, none of our basic techniques tell us how we can solve that integral. So let's go ahead and use the calculator here. Functional integration 0 to pi. And then I need some parentheses here, cosine, 1 square root. Going too fast. Delete this. Square root of 1 plus, now I need some parentheses, cosine of x squared. Close those parentheses for cosine squared of x. Parentheses are already closed for the integral dx. There we go. Let's approximate this to be 3.820. Part C. All right. Moving right along to number 33. Y is equal to 10 e to the x over 10 plus e to the negative x over 10. Negative 20 less than or equal to x less than or equal to 20. This is based off of a function that we talked about a little bit in chapter 5. You may not be familiar with it, so I'm going to go ahead and refresh you here that there's hyperbolic sine of an argument u is equal to 1/2 of e to the u minus e to the negative u, and hyperbolic cosine of u is 1/2 of e to the u plus e to the negative u, or you can do e to the u minus e to the negative u over 2 if you prefer. And e to the u plus e to the negative u over 2. Those are important functions for us to know later in math. This is a form of that I can say that 10 is half of 20, and then it fits the form of u being x over 10. So I'm going to rewrite y as, since it's got the plus here, I'm going to write it as 20 hyperbolic cosine of x over 10. Why am I doing that? Because derivatives are so easy with hyperbolic trig functions that the derivative of hyperbolic cosine is hyperbolic sine, and the derivative of hyperbolic sine is hyperbolic cosine. So leaving the 20 constant multipliers alone, derivative of hyperbolic cosine is hyperbolic sine, and function times the derivative of the inner function. 10 cancels with 20 and makes it 2. So this is 2 hyperbolic sine of x over 10. So now when I want to find my arc length. And by the way, there's a picture for this situation here. This is a catenary of a cable, probably an electric cable connected between two towers here. And it has the minimum of the cable at x equal to 0. And it has one of the towers. This is right in the middle here, and one of the towers on the left side and one of the towers to the right side. That's why we're equidistant -20 to 20. And notice that this function here has y-axis symmetry. That might be important to us in a little bit, but this is related to the hyperbolic cosine function. So let's go ahead and look here at our integral goes from -20 to 20, root 1 plus 2 hyperbolic sine of x over 10 quantity squared see what I did wrong. Oh, I wrote over 10. This is over 20. This is 10. This is 20. Yeah, those were supposed to go away. Over 20, over 20, over, this goes away, and this is over 20, and this is over 20. There we go. That looks better to me. I'm not supposed to have any constant multiplier left inside of there. So this is 20, and this goes away completely. All right. Looking much better. So this is -20 to 20, root 1 plus hyperbolic sine squared of x over 20. And this is dx on the end. All right, so you don't know hyperbolic trig identities probably, but your Pythagorean identity for hyperbolic trig functions is 1 plus sinh squared u is equal to cosh squared u. So this turns into s is -20 to 20 of root cosh squared x over 20 dx. And so this is s is integral -20 to 20 of cosh, sorry, no square root anymore, cosh x over 20. Now I already showed you a picture of what the hyperbolic cosine function looks like here, and it has y-axis symmetry. So we can get the same answer here by going 2 times 0 to 20 hyperbolic cosine of x over 20 dx. So now we need to multiply by 1 over 20 on the inside and 20 on the outside. Hyperbolic cosine of x over 20, and that's going to give me hyperbolic sine of x over 20 evaluated from 0 to 20 is going to give me 40. Hyperbolic sine of 1 minus 40 hyperbolic sine of 0. Hyperbolic sine of 0 is 0. It goes through the origin. So s is equal to 40 hyperbolic sine of 1, which is approximately, well, let's turn this back into the statement, 40 times 1/2 e to the first minus e to the negative first, right? So that will be s is 20 times e minus 1 over e, approximately 20 times e minus 1 over e. And that is 47.008. And then these are meters in our problem, so we need to put units with this. Now there is a hyperbolic sine and hyperbolic cosine function in the calculator, but it's hidden in the catalog. So if I wanted 40 hyperbolic sine, I have to go to the catalog and look under S and then scroll down. There it is, of 1. I get the same answer because those functions were equivalent. So it's kind of a pain to find hyperbolic sine and hyperbolic cosine in the calculator. I wish that it was a little easier, but I don't think they want you to get it confused with sine, cosine, and tangent. So there it is. All right, let's look at number 39. And we start to do surface area of solids of revolution here. So I'm going to use capital S to represent surface area, and that's going to be equal to, and I'm going to have the same square root that we've been talking about 1 plus y prime squared dx, integral here from a to b, but there's going to be an extra piece here, and it's going to be a y, or an f of x, if we are revolving about the x-axis. Capital S is going to be a to b x root 1 plus y prime squared dx. This is our multiplier here if we are revolving about the y-axis. So our first problem here revolves about the x-axis. So we'll be using that first formula, and we'll need to multiply by our original function in our setup here. So capital S is equal to, and we're going from 0 to 3. We see that on our graph. And we need our y, which is 1/3 x cubed square root of, and our derivative y prime is going to be x squared. So 1 plus x squared squared is x to the 4th dx. So u is equal to 1 plus x to the 4th. du is 4x to the 3rd dx. So I'll pull the 1/3 out, multiply by 4, and multiply by 1/4, all in one step there. If that is there, then S is equal to 1/12. Oh, and I forgot there's also a 2 pi multiplier in front of these. I apologize, because they're based off of the shell method. So S is 2 pi times S is 2 pi times. Okay, so integral of u to the 1/2 du, and u is 1 to 82. There we go. I got the formulas right, and I was so excited about telling you which multiplier, I forgot to write my 2 pi in the formula. I'm sorry. So 2 into there, S is pi over 6, and then this is u to the 3/2 times 2/3, 1 to 82, and that is 3. So this is pi over 9 times 82 to the 3/2 minus 1, and S is approximately pi over 9 times 82 to the 3/2 minus 1, 258.85 is sufficient for the answer that the book gave. So let's continue with number 45. And notice now that it says that we're going to revolve around the y-axis. So we're going to have that multiplier of x now. So y is equal to cube root of x plus 2. X is between 1 and 8. So y is x to the 1/3 plus 2. Y prime is 1/3 x to the negative 2/3. So capital S is going to be 2 pi integral 1 to 8 of x square root 1 plus y prime squared is 1 over 3x to the 2/3. This is 1 over 9x to the 4/3. So S is 2 pi 1 to 8x square root of 9x to the 4/3 in the bottom, 9x to the 4/3 plus 1 in the top. That is going to be capital S is 2 pi 1 to 8 of, I'm going to put my x over here because I'm pretty sure that it's going to end up being part of du, 3x to the 2/3 root 9x to the 4/3 plus 1. We'll pull that 3 out. 1 to 8. X divided by x to the 2/3 is x to the 1/3 dx. Root 9x to the 4/3 plus 1. Okay, so u is equal to 9x to the 4/3 plus 1. That makes du equal to 9 times 4/3, x to the 1/3, 3 goes into 9 3 times, so this is 12, x to the 1/3 power. So I need a 12 on the inside and a 1/12 on the outside. That makes capital S equal to pi over 18. 2 goes into 12 6 times, 3 times 6 is 18. And then this is going to be u to the 1/2 du. And let's see, u substitution. So 9 plus 1 is 10. 2 to the 4 is 16. 9 times 16 plus 1 is going to be 145. So this is going to be S is equal to pi over 18, u to the 3/2 times 2/3, as u goes from 10 to 145. This is 9. S is pi over 27 times 145 to the 3/2. I promise you that doesn't break down anymore. And 10 to the 3/2, that doesn't break down anymore. I could make it 145 root 145 and 10 root 10, but it's the same thing. So clear. Clear. We have pi over 27 times 145 to the 3/2 minus 10 to the 3/2, and I get an approximation of 199.48 for my surface area. So arc length would be measured in units. Surface area should be measured in square units. I don't think that I wrote that earlier, but your volume should be measured in cubic units. So let's go ahead and look at number 47. So 47 is y equals 1 minus 1/4 x squared. I'll write it that way instead of x squared over 4. X is between 0 and 2 inclusive, so y prime is going to be negative 1/2 x. And I, again, am revolving around the y-axis. So capital S is going to be 2 pi integral from 0 to 2 of multiplier of x square root of 1 plus this thing squared is 1/4 x squared dx. So I'm going to make this 1 equal to a 4 over 4. And capital S is 2 pi 0 to 2. Put my x over here with my dx where I think it's going to belong. And this is going to be x squared plus 4 over root 4. Let me make it clear that the square root is just in the top. So root 4 is 2. This 2 cancels with that 2. And capital S is equal to pi 0 to 2 of root x squared plus 4 x dx. I think I can get this without a whole u substitution and changing my limits. The derivative of the inside is 2x, so let's balance that out with a 1/2 there. And let's go at it from there. So this is pi over 2, and this is x squared plus 4 to the 3/2 from 0 to 2. So S is equal to pi over 2, and then evaluate this. 4 and 4 is 8 to the 3/2. 4 to the 3/2 is 2 to the 3rd is going to be 8. So I can pull an 8 out of this and make this 8 pi over 2 or 4 pi, and then square root of 8 minus 1. I forgot. This is 3/2, so this is 2/3. So this is over 3. And this is over, let's see, this is 8 pi over 3. That's what I get for not doing my U substitution. So, all right, so 8 pi over 3, and then square root of 8 minus 1. Capital S is approximately 15.318 square units. Let's look now at number 65 to wrap things up. Scroll a little bit here. All right. So a picture will be helpful for us here for 65. And we have a object that is fleeing, that's traveling, let's say, due north here on our coordinate axis. It's traveling straight up the y-axis. It's trying to run away in a straight line there. And as it's doing that, its pursuer, which starts over here, 1 unit, let's say, east of the original point of the pursuer, is always facing ahead of it slightly. It's turning towards it, let's say. So how do they say this? They say at the same time the pursuer leaves point 10, it always moves towards the fleeing object. So as the object is moving north away from it, the pursuer is always moving in this path where it's facing the object. Now, we know that the pursuer is going to have to travel faster than the fleeing object to be able to catch it here, because it's going to have a longer distance to travel this curved path than the straight path. They're telling us in the problem how much faster in this example, that the pursuer speed is twice that of the fleeing object. So when it catches it, it should have traveled twice as far as what they're telling us. But let's go ahead and prove all that with calculus now. So first, the easy part is let's figure out the y-intercept of the path that the pursuer takes. X to the 3/2 minus 3x to the 1/2 plus 2 has a y-intercept of 1/3 of 0 minus 0 plus 2 is 2/3. Since the pursuer and the fleeing object are going to have the same y value when the fleeing object is caught by the pursuer, then we can say that the fleeing object traveled 2/3 units along the y-axis before it was caught by the pursuer. Okay, so that's the first part of me figuring out how far the fleeing object traveled. Now I need to prove with calculus that the pursuer traveled double that. So y prime is going to be 1/3 times 3/2 x to the 1/2 minus 3/2 x to the negative 1/2. So y prime is 1/3 times common factor 3/2 x to the 1/2 minus x to the negative 1/2, and that's going to be y prime is 1/2 of, and I'm going to multiply by x to the 1/2 over x to the 1/2 here to get rid of the um, fraction, or get rid of the negative exponent. So this is going to be x minus 1 over 2x to the 1/2 for my y prime. Now, arc length of the pursuer is traveling from 0 to 1. It's the same path as traveling from 1 to 0. It's the same distance, but I'm going to put 0 to 1 in there. And this is going to be square root of 1 plus, and then this thing squared. So x minus 1 squared over 4x. So I'm going to make this 1 into 4x over 4x dx. So that makes s equal to 0 to 1 of, and then the 4 can come out as a 1/2. And this is square root of x down here. And this is going to be square root of 4x plus x squared minus 2x plus 1 dx. And so that is going to be, s is 1/2 of 0 to 1 of square root of x is down here, root, let's write this in descending order, x squared plus 2x plus 1 dx is 1/2 0 to 1 of root x plus 1 quantity squared over square root of x dx. So s is 1/2 0 to 1 of x plus 1 over root x dx. So that makes two integrals, 1/2 0 to 1 of x to the 1/2 dx plus 1/2 0 to 1 of x to the negative 1/2 dx. And s is equal to 1/2 x to the 3/2 times 2/3 from 0 to 1 plus 1/2 x to the 1/2 times 2 from 0 to 1. And this is, s is 1/3 of 1 to the 3/2 minus 0 plus 1 to the 1/2 minus 0. So s is equal to 1/3 times 1 plus 1, which is 1/3 plus 3/3 is 4/3, which is 2 times 2/3, which is how far the fleeing object traveled, was 2/3, and the pursuer traveled twice as far. So we have shown that the pursuer traveled twice the distance of the fleeing object here. When the pursuer catches the fleeing object. So at that point in time, exactly at that point in time, the pursuer has traveled twice the distance of the fleeing object, which makes sense because they are getting to the same point and in the same amount of time, and the uh, pursuer is traveling twice as fast, so it needs to cover twice the distance in the same amount of time to get to the same point as the fleeing object at the same time. All right, that's it for uh, this video. We'll come back next time and talk about 7.5, which is going to be integrals that involve work done by a variable force. We'll talk a little bit about work done by a constant force as well, but mostly we'll talk about work done by a variable force. So see you for the next video.